Hello everyone, my name is Tatus Polakori from Pebble Education. Today we're going to talk about the basics of the statistics for data science. This is the first video in our data science course and we have many more planned for you. What is statistics exactly? Statistics is a branch of applied mathematics and it's used nearly every day by data analysts and business intelligence professionals to find trends and patterns, specifically in things such as sales and customer data. But statistics is not only limited to business and finance and can be used for a wide variety of situations. Having good statistics knowledge is crucial to becoming successful in a data analysis career. Here are the things we're going to talk about today. We're going to start off with some very basic terminology in statistics, and then we're going to move on to some advanced terminology that's used specifically in data analysis. And then we're going to end off by talking about some popular types of graphs to use in data analysis. First off, mean, median, and mode. Now, this is one of the most basic things you can learn, and also one of the most important. Now, you probably already know a lot about this, so I'm going to go over this fairly quickly. Mean is the average of a data set, and to find the average, you have to add up all the values together and divide by your number of values. Your median is simply the middle value in a data set, and the numbers have to be put in ascending order before you can find your median. Your mode is the value that appears most frequently in your data set. So in this example here, the mode would be the number 5 because it appears the most. Now let's just go on to some more advanced topics. Standard deviation. Standard deviation basically tells you the spread of a data set. So a low standard deviation means that the data points are less spread apart, and a high standard deviation means the data points are more spread apart. And to calculate the standard deviation of a data set, you first have to find the mean of the data set. So you have to pick a column. If it's multi-column, you have to pick a column and find the mean of that data set. Then you calculate each deviation by subtracting the mean from each data point to find the deviation of each value from the mean. Then you square each deviation to make sure that negative values don't cancel out the positive values. Then you find the average of the squared deviation. So you essentially find the mean of the squared deviations. And then you find and the value that you get when you find the average is known as variance. And then you have to take the square root of the variance. Now, because it's a very resource intensive process and takes a lot of time and effort, lots of programs such as Excel and Tableau have these built into their systems so it can save you time and you can focus on other things. Next, we're going to talk about regression. So regression is essentially the relationship between the independent and dependent variables, and there's many different types. So I'm going to talk about linear regression real quick, which is a straight line. So with linear regression, you have something known as the coefficient, which is also the slope, and it basically tells you the strength and direction of the relationship between variables. So say you have a scatter plot where the data points are generally pointing to the top right of the graph. This is known as a positive correlation, and the coefficient of a linear regression model in this graph would be positive. Residuals are the differences between the observed values and the values predicted by the regression model. So a good regression model will have small residuals and they'll be randomly distributed, meaning that your model is working efficiently and has a good fit. Now, similarly, R squared is a measure that tells you how your model fits your data. So an R squared value that's closer to 1 shows a better fit. Now, there's many other types of regression models, and the two main other ones are exponential and logarithmic. So let's go over to my whiteboard and we will see the differences. So essentially, a exponential model has a graph that moves something like this. And this is an exponential function. And if your R squared value is closer to 1 for this graph, let's say your R squared value is close to 1. That would mean the data points in your data set follow this pattern or something similar to it, which means that all your data generally fits. And now you'll see that I actually made a data point over here. This is what you call an outlier. And in this situation, you wouldn't count that into your linear regression or your regression model, sorry. And the other type of regression model that's commonly used is a logarithmic regression model, where it sort of plateaus around starting around here. Now, again, your R squared value, if it was close to 1, that means your data would fit this line very closely. And as you notice, both of these have a positive correlation. However, you can have linear, exponential, and logarithmic decay. And exponential decay looks like this. And again, with the r squared values closer to 1. But for this, if you have an r squared value that's closer to 0 than it is to 1, that means your data is generally scattered and not a good fit with the line. And if you have multiple outliers, this can be the case. Sometimes the number of outliers you have impacts your r squared value. So this would be a data set which, yes, it does generally follow the exponential decay pattern, but also has a bad r squared value because of the spread of data being extremely far apart. Now, if we go back to our slideshow, we can see some other types of models. So these are some of the graphs that I made. On the left-hand side here, you have a logarithmic regression model. And as you can see, again, it plateaus off, and that is the key characteristic of a logarithmic graph or logarithmic function. On the right side, you have a graph with a linear regression model put onto it, and you can see that the coefficient of this blue line stays the same throughout the whole graph, and generally it predicts it predicts a pattern of the data set into the long-term future. Now, let's move on to some common graphs that are used in data science. So, one of the most common graphs used in data analysis is a bar graph, and this can be really useful if you want to compare percentages or quantities of an item, let's say. Now, in this example, I have various cities on this graph: Los Angeles, New York, Philadelphia, and Tampa. And on the y axis, I have total rainfall in inches in 2019 for each of those cities. Now, as you can see, this is very useful to compare different cities. Los Angeles, for example, had around 7 inches of rainfall in 2019, whereas Tampa had around 62 inches of rainfall. Now, what you can conclude from this is that Tampa would generally be a more humid location. And if you were to investigate into this graph further or into this data set further, I'm sure you would find that's the case. Now, moving on to a line graph. This is one of the most simple graphs you can make and is very useful to observe changes in one variable over time. So in this graph, I have various countries and their GDP per capita from the years 2000 to 2020. Now, as you can see, these dashed lines are my regression models, and I have linear regression models put in for every single line. Now, as you can see, the trend for a country such as the United States generally goes upwards. And my r squared value for this, if I remember correctly, is around 0.997. That means my r squared value, that means my data fits my linear regression model very well. Now, if you were to compare that to something like Japan, for example, which is this yellow line here, the r squared value is around 0.147. That means the regression model does not fit the data at all. And that is very visible here because you have very extreme dips and valleys in this data. And that was caused by many reasons, which we will get into as we analyze this graph further in the next episode. So box and whisker plots, these are another very common graph that's used because they allow you to summarize a data set very quickly. So essentially how you read a box and whisker plot are there's many ways to read a box and whisker plot. The first thing I look at when I'm presented with a box and whisker plot is the range of data. So this is the average percent of humidity for a country or for a city, I believe it's Houston, in a certain year. So if we look at 2014, let's ignore 2013 for now because that's when they started collecting the data and it's not a full data set. If we look at 2014, which is the first full year that they collected this data, you can see that the minimum value goes to around 38, 39%. And the maximum value goes to around 91 or 92%. Now, we will choose to ignore these outliers that are outside the range. And if we look at the rest of the graph, this line here is a median, which tells you generally like where the middle of the data is and how like spread apart it is. That's also an indicator of how spread apart it is. And this line right here is your first quartile, and this line right here is your third quartile. Now, if we keep looking at different years, you can see that 2015 generally had a much larger range of data points than 2014, while also having less outliers. So in 2015, you can see that the lowest average humidity was around 36, and the highest was around 96 or 97. Now, what that tells you is in the year 2015 in Houston, the average percentage of humidity was higher. And with that information, what you can do, you could go and research the causes of higher humidity. For example, maybe there were some more natural disasters like hurricanes or something like that. But basically, a box and whisker plot allows you to find very simple patterns in like range specifically and allows you to go into more depth and research about what could have caused that. That's going to be all for today. Please stay tuned for more videos coming out about this topic, and thank you for watching.